Hi, my name is Anthony Rizzo, and today I'm going to be giving my lab report over Physics 2212 Lab 5, Magnetic Braking with Faraday. I'm going to apologize in advance for my voice. I happen to have a cold right now. So the purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, to model the magnetic tube interaction computationally and compare your computational predictions with your observed data. Quick preview of my results, found that the actual average time taken was 1.48 seconds versus the computational model time taken, which is 1.545 seconds. So some of the key physics principles used include Faraday's law, Ohm's law, the Biot-Savart law, magnetic field of a bar magnet, magnetic flux, and using the momentum principle. Here are some of the relevant formulas that we're going to be needing to carry out some of our later calculations. So for our procedure, first we wanted to mark which side on the magnet is facing north, record the dropping the magnet through the aluminum foil tube. Next, scrub through the video to find the entry and exit times. Repeat this process then 5 times in order to find the average time taken. So here's the initial experimental data that we found, including the length of the tube, the inner radius of the tube, width of the foil, the magnetic dipole moment of the magnet, and the mass of the magnet, which we're going to be needing to create our computational model. So speaking of that, getting right into it, the first part of the computational model includes setting up our physical constants, which you can see. Next, step one, we're computing the geometry of the tube by inputting our experimental data. So next, we are creating the bar magnet. So first, we input the properties of the magnet, which we found. Next, we want to be able to visualize the bar magnet in our model. So we have to enter the information in order how to do that, which you can see. Next, in step two, we're creating a function to calculate the magnetic field of the bar magnet, which you can see right below that. For step three, we want to calculate the magnetic flux, which you can see in this equation or in the function that I created below. And then step seven is just one line to calculate the gravitational force on the magnet. Step four, we want to calculate the current in the ring, which you can see. For steps 5 and 6, we edit the lines to compute the B field, which you can see how we did that there. With step 7, we're calculating the net force on the magnet. And step 8, we're updating the magnet's velocity and position by applying Newton's second law. And that is it. So then with the results of our glow squared model, you can see here. And so now to interpret the simulation, which color corresponds to clockwise as viewed from above and which counterclockwise? So thinking about this in terms of using Lenz's law, red is counterclockwise and blue is clockwise, as this will create the force to slow the magnet down. What happens to the dynamics of the system when you flip the magnet around? Essentially nothing, but the currents will now flow in the opposite direction if you're looking through the same side. How does the total time in the tube, your real world system, compare? Um, This model was fairly accurate, but in order to make it more accurate, we could split the tube into more rings to get a more accurate result. And what is the shape of the velocity versus time plot? Tell you about the forces acting on the bar magnet. The forces acting on the magnet are unbalanced where the graph is not constant, and you can see that here in this section here and this section here. It is not constant, so the forces are unbalanced. And finally, we have our discussion questions. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics change? So the induced current will approach infinity, and because of this, the braking force will increase to match the force of gravity, which will prevent the magnet from falling any further through the tube. What if holes or slots were cut into the tube? How would this affect the ring in the model? There would be a reduced amount of current flowing through the tube, which means the braking force would be weaker. Therefore, the magnet will fall faster through the tube. Thank you.